Hello everyone. Today we're going to be solving this ODE using Laplace transforms, and we're actually going to be using a specific method called completing the square. Now, for those of you who aren't familiar with Laplace transforms, it's essentially a method to transfer a time domain function into a frequency domain function to make solving ODEs easier. Now, let's get started. So the first thing that we can do is we can start to take the Laplace transform of our given ODE. So we'll have essentially this calligraphy L followed by a curly bracket of y double dot to denote the Laplace transform. And then we'll have plus 8 times the Laplace transform of y dot. And notice we can pull the 8 out because 8 is a constant. And then we'll have plus 20 times the Laplace transform of y. And that'll be equal to 0. Now, based off of the relations that we have for y double dot, and y with the Laplace transforms, we get s squared times capital Y of s minus s times the initial y position minus the initial y velocity. And notice this y naught and then y naught dot, they're both given up here. So we'll plug those in later. And then we'll have plus 8 times s times capital Y of s, where I should say y of s is our frequency domain function after transferring our time domain y function. And then we have one more piece. We have our initial y position again. And then we'll have plus 20 times capital Y of s equal to 0. Now, the next step that we can do is we can pull out the capital Y of s such that we get s squared plus 8s plus 20. And then after plugging in our y0 and then y dot 0, we also have a minus s and a minus 2, and that's going to equal 0. Now the next thing that can be done is we can essentially divide this s squared plus 8s plus 20, and then we can add over our negative s and negative 2 terms, such that we get capital Y of s is equal to s plus 2 divided by s squared plus 8s plus 20. And then this is where the completing the square method comes in handy. So we'll leave the numerator the same for now, but then we'll set up this kind of format where we have something in parentheses squared plus something squared. Now in these parentheses, we're going to have this s here. And the question is, what should we put in this next space? Well, what I like to do is I like to look at the s term here and then take whatever that coefficient is and divide it by 2. So in this case, since we have 8, we'll divide that by 2 and we'll do s plus 4. Because if we were to actually expand this here, we would get s squared plus 8s plus 16. Now, in order to make these two equations the same, all we're missing is this plus 4 here. So what we can actually do is we can write that plus 4 over here as 2 squared, such that we have the exact same denominator that is equivalent. So that's essentially the start of completing the square method. Now the next thing that we have to do is we have to get a little bit tricky with our numerator. So what we can do is we can say we have s plus 4 minus 2, and then denominator we will leave the same. Now, the reason that we did this, where we have the s plus 4 minus 2, is so that we can actually split up the numerator. So we can write it out like this now. So we have s plus 4 divided by s plus 4 squared plus 2 squared. And then we'll have minus 2 divided by s plus 4 squared plus 2 squared. Now the whole reason we did this is because we actually have two inverse Laplace transforms that will solve basically our ODE. It'll solve each of these. So now the first one is the inverse Laplace transform of s plus a divided by s plus a squared plus omega squared. Well, that's going to be equal to e to the negative a times t times cosine of omega t. And now the other one that we're going to use is inverse Laplace transform of omega divided by the s plus a squared plus omega squared. Well, that's going to be equal to e to the negative a times t all times sine of omega t. So now all we have to do is just pair up what our variable a and w are. So in this case, we can see that a is going to be 4. We also have another case here. And then omega is going to be equal to 2 here. So let's write that out on the side here. So we'll say let a equal 4 and omega equal 2. So now when we take our inverse Laplace transform and we translate back to y at t to solve it, so that'll essentially be our inverse Laplace of capital Y of s, again, because we're transferring our frequency domain function back to our time domain function, and then that's going to be equal to, we'll essentially just plug in these equations. So we'll start with this one first, which corresponds to our e to the negative at cosine omega t. So then we'll have e to the negative 4t, because we said a is equal to 4, times cosine of omega t, where we said omega is 2, so we have cosine of 2t, and then minus, and then for this term, that will correspond to this e to the negative at times sine of omega t. So then we'll have e to the negative 4t times sine of 2t. So now you know how to complete the square to essentially solve ODEs using Laplace transforms.